Hi, I'm Charlie Mione, and I'll be presenting BabyNet, a residual transformer module for birth weight predictions on fetal ultrasound videos. So the problem statement, predicting fetal weight at birth plays an important role for perinatal care, along with gestational age and complications in pregnancy. These can help choose the method of delivery, whether it's natural or cesarean. And this is just a picture of an ultrasound. Right now, fetal birth weight is estimated using the head circumference, the biparietal diameter, abdominal circumference, and femur length, which you can see these are pictures of an ultrasound showing all of those. And unfortunately, this estimate is often imprecise with up to like a 10% mean absolute percentage error. And because these measurements, they require the fetus to be highly visible. And so that's why there's some error. Some related research, ensemble methods that create multiple models are a very good technique for prediction, since they increase the diversity of the algorithm and they reduce generalization error, which improves the results accuracy. The random forest is a type of bagging algorithm that reduces the variance. XGBoost is a boosting algorithm that reduces the bias. And LightGBM is a gradient learning framework based on tree learning. So in this study, voting is used to construct an ensemble model. For this study, they use a hybrid LSTM network model for temporal data analysis, which is the long short-term memory networks is what that stands for. And so it combines multiple electronic medical records with ultrasound examinations of pregnant people to construct a hybrid birth weight predictor classifier based on that network. And the data for this was collected from 5,759 Chinese pregnant women who have given birth. And that resulted in 57,000 records. And this is another related research, which is just convolutional neural network based models. And they also proposed to estimate fetal weight based on ultrasound images. The motivation behind researching this is that these methods that I just listed, they don't rely on true fetal birth weight as the ground truth. So instead, they predict using the estimated body part measurements that I was previously mentioning, which is prone to error, like I said. The main contribution of this paper is an end-to-end method for birth weight estimation, which is based on fetal ultrasound video scans. They also give a novel residual transformer module by adding temporal positioning to a 3D multi-head self-intention in 3D ResNet-based neural networks. And then to the best of the author's knowledge, BabyNet is the first framework to automate fetal birth weight predictions on ultrasound scans, and it was trained and validated with data acquired 1 day before delivery. So that would be the most accurate birth weight. This is an overview of BabyNet for fetal birth weight estimation from ultrasound scans. They replaced the 2 residual modules of 3D ResNet 18 with 2 residual transformer modules that have 3D multi-head self-attention, which you can see in the dark green, which I don't know if you can see my cursor, but these dark green is where they replace it. And this contains relative positional encoding. Relative position encoding, RPE, is calculated with the sum of the 3 parameters above, which you can see up here. And that is the height, width, and temporal positioning encoding. This model takes 16 frames, which you can see on the bottom left, as the input to make a single segment prediction. And they're divided into non-overlapping frame segments. And then the prediction is made by averaging all of these predictions together. So feature extraction. The ResNet 18 is the convolution neural network that is 18 layers deep, And this is the base network to extract high-level 2D plus T spatio-temporal ultrasound feature representations. So this is the initial input, where H is the height, W is width, and T is the frame number. And it's transformed via convolutional residual models to a low resolution feature map, which you can see it's transformed here, where T is the original frame number divided by 4. H is the original height divided by 8, and width is the original width divided by 8. And these feature maps are fed into the residual transformer module that we'll be talking about next. So these modules are made from a layer followed by a rectified linear unit and then a batch normalization. And this is repeated 2 to 3 times. The RTM extends to 3D spaces by adding that position encoding that I was talking about previously to the 3D multi-head self-attention, which we'll be discussing next. With that being said, the RTM is defined as the equation here, which you can see as X being the input, Y being the output, and con denoting the convolutional layer. Bn is the batch normalization, and then sigma is the RALU. To learn multiple attention representations at different positions, instead of performing a single attention, we do many self-attention heads, and then they're trained and their outputs are concatenated. So since the model doesn't assume spatial relationship between the features, positional information needs to be added. So like mentioned in the overview, the sum of the RH, RW, and RT are used to find the positional encoding, which is R in this case. And then the 3D multi-head self-attention is computed with the equation that is seen here. QI are the queries, KI are the keys, and then VI are the values for the ith attention head that are calculated from the 2D convolutions. And then these outputs are concatenated, as I previously mentioned, to compute the MHSA. The dataset used in this experiment consisted of 225 2D fetal ultrasound video scans in a standard plane, which you can see an example down below. And it's the view of the head, abdomen, and femur. You can see in these pictures that they're pretty low quality because they're towards the end of the pregnancy, so there's less amniotic fluid. The dataset was obtained by from 75 pregnant people from the ages of 21 to 42, and they were collected just through routine ultrasounds that happened less than a day before delivery. Each ultrasound is captured in 2 resolutions, 960 by 720 and 852 by 1136. And the number of frames is between 463 and 1448, with an average of 852, and the FPS between 24 and 37. And as the ground truth, they used the true weight of the baby at birth, and these values were between 2,085 and 4,995 grams, which is about 4.6 pounds to 11 pounds, which I previously mentioned that those other methods didn't use this as the ground truth. They didn't use the true weights. So the implementation, like I previously stated, they adopted the 3D ResNet 18 as the base neural network. So pictured is a table comparing the 3D ResNet 18 with BabyNet. And so you can see during the last stage, they replaced the residual modules of 3D ResNet 18 with the residual transformer modules that have the MHSA. And the output of the final RTM is global average pooled gap and is fed into the fully connected layer with 1 neuron for the fetal birth weight prediction. This model was implemented with PyTorch and is trained using the NVIDIA RTX 2080 Ti. And during training, they applied data augmentation, which included rotation, randomizing brightness and contrast, horizontal flipping, image compression, and blur. comparing BabyNet with several 2D plus T spatiotemporal video analysis methods. They used mean absolute error, root mean square error, mean absolute percentage error. They're used in comparison. So the first method listed here are results from a clinic in Israel. And the second results are obtained by the clinicians that work with them for the data set. And then the third is the result of video vision transformer. The fourth is a hybrid of 2D ResNet 50 and the video vision transformer that I mentioned before. And the fifth is the base neural network without the replacement of the 3D ResNet. And then finally, BabyNet. The researchers didn't detect a significant difference between the first method, the clinicians from Israel, and their algorithm. The estimations from the dataset seem to be better than those of BabyNet. So, but out of all the neural networks, BabyNet outperformed them. So the researchers decided to take the average of the clinicians that they worked with for the dataset and BabyNet and found that those results were much better than any of the other ones, which you can see here. We want to minimize the error, and so the clinicians in BabyNet have the smallest. They also did an ablation study to see the effectiveness of the components that they added to the base method. So you can see here, the base neural network is improved when they replace the last layer with the RTM, and that has the MHSA, and then it's further improved by adding the temporal position encoding, as you can see here. Discussing, so the comparison with the clinicians varied. As you can see, the clinicians from Israel, they outperformed, but they didn't outperform the clinicians that they worked with. And so they stated that the clinicians that they worked with for the data set were top experts in performing these measurements. So they believe that BabyNet may outperform, say, an average expert that you would see in hospitals that do these measurements all the time. The method presented is end-to-end, and so it reduces the workload of, performing these estimations. And this should be seen as more of an aid for clinicians in their decision to whether or not have a natural or cesarean birth, because heavier babies may pose a threat to both the person pregnant and themselves if they're delivered naturally and they are too big. The data set presents are very limited. Like I said before, the data set is really small. And so BabyNet doesn't know how effective it would be with a bigger data set. And the population is very specific. They didn't have varying races in the data set. So they're not really sure how that would apply to, say, the United States, who has varying races, ethnicities, and nationalities. Like we said in the previous slides, this method averaged with clinician data outperforms the top experts' predictions. And this method can assist with making an important decision that affects both the mother and the baby's health. These are some of the strengths and weaknesses that I found. The author makes it really clear as to why it's important to have accurate measurements of the birth weight of both the fetus and for the health of both the fetus and the mother. But there's not much discussion on previous studies on this. And I don't think it's because of the lack of research on this topic, because I was able to find many resources, but they just did not discuss it in the paper. As discussed previously, the data set is very limited and small, and there's not much variety in the pregnant people's race, ethnicity, and nationality. And what that means, there's not a lot of variety in people's medical history or lifestyle. And so we're not really sure how BabyNet would react to something like that. And so for this reason, I gave this paper a 4 on the NIPS reviewing scale. I'd probably lean towards rejecting this study right now because there's lack of testing. And I do think it's important for the health of pregnant people, but it could pose a problem if not tested on different races, ethnicities, and nationalities. Right now, this is early accepted into the Singapore Medical, I forgot the long name, I'm sorry, I'm drawing a blank, but
Nikai, right?
yeah, but I believe that there should
Yeah.
probably be more studies.
Yeah.
These are just some additions that I would add. As talked about in the previous slide, I think the study needs to be expanded. Their data set significantly small and only contains one ethnicity group. I also posed the question is whether or not this high level of accuracy is needed. I tried researching like mortality rates of women and babies relating to birth weight, and then even not even complications that didn't result in death. And I couldn't really find much of this data. I was thinking it could be because either A, it wasn't a very big problem because, you know, we've been giving birth for millions of years, but also with the experts' prediction, I was thinking that maybe the data wasn't recorded like specifying birth weight. Instead, you know, it was spread into different categories such as like obstructed labor, which is not always due to a large baby. So we can't just assume that that's the reason. So we can't use that data. These are some of the resources that I used that weren't in the paper. Yeah. Thank you.